Hello, my name is Teresa and I'm an undergraduate researcher in Dr. Bacrenzio's neuroengineering lab. My project is titled Comparative Analysis of Neural Recordings from Intracortical Arrays in Anesthetized and Awake Rodents. So intracortical microelectrode arrays, or MEAs, are promising tools for the study of brain function and development of neuroprosthetics. These MEAs are able to detect and record the electrical signals generated by the motor cortex. Now, the motor cortex is generally associated with movement, so it's logical to assume neural recordings should be done while the subject is freely moving. However, most studies have observed spontaneous firing of neurons while subjects were under anesthesia. This brings up the matter of whether or not anesthetized neural recordings can provide some advantages and/or yield similar data to awake neural recordings. In the study, we used active electrode yield, or AEY, and signal-to-noise ratio, or SNR, to measure the performance and reliability of the MEAs. The goal of the study is to investigate whether there will be a significant difference in neural recordings for MEAs connected to the motor cortex while anesthetized under isoflurane or awake and freely moving. Here, the MEA device being used is a single shank probe aligned with 16 iridium electrodes as depicted in Figure 1A. The MEA was implanted 2 millimeters into the motor cortex for a total of 7 rats. After the surgeries, the animals were given 1 week to recover, and at the 2-week mark, neural recordings were conducted. For each animal, 10-minute recordings were performed for both anesthetized and awake states. After processing the data with the bandpass filter, signals were detected with a threshold of -4 times the root mean square of noise. Figure 2 showcases a representative unit from one electrode site during a neural recording. In this particular instance, there are 2 noticeable units that highlight the desired depolarizing and repolarizing waveform. Active electrode yield was defined as the percentage of electrodes displaying discrete neural signals, and signal-to-noise ratio was defined as the signal's peak-to-peak voltage divided by the RMS noise. Now I would like to discuss the results for the performance measures of MEA. Remarkably, there were no significant differences observed in AEY. Several electrode channels gained or lost detectable units during the transition to an awake state. Previously, some channels had no detectable units while anesthetized and began showing units in the awake state, while others lost all detectable units in the transfer. Shown in Figure 3A is a representation of the activity of electrodes under each condition and quantified as percentages in Figure 3B. One thing to note is the number of units showing per electrode. The amount of units is negligible when considering AEY. If no units are detected, the electrode is inactive. Anything greater is simply classified as active. In the bigger picture, a 2.09% decrease in AEY was considered statistically insignificant. The other important measure is SNR. From anesthetized to awake, there was a significant 21.6% decrease in SNR. This is largely due to the 48.6% increase in noise for the awake condition. A higher amount of noise indicates a lower or worse SNR value. A higher or better SNR will allow for easier detection of signals overall. Now, there are some important differences in the neural recording plot between the 2 conditions depicted in Figure 4. The awake recording has a lot more noise but also has an increased frequency and spike. Although the higher frequency of spikes is promising, the overall SNR is a better indicator of how well the probe functions. The peak-to-peak voltage also contributes to SNR. Figure 5 highlights the peak-to-peak voltage changes between the 2 states. Importantly, a higher amplitude was observed at both the wave's trough and peak under the awake condition. The 14% increase observed was marginal yet significant. Due to an increase in noise, the SNR decreased significantly, despite a small increase in VPP. From this study, a significant increase in firing rate between the 2 conditions was expected. A surprising result was the depth dependency of the change in firing rate. The probe was divided into 3 groups: the upper 5, the middle 5, and the lower 6 electrodes. Notably, the upper and lower electrodes had a greater increase in mean firing rate than the middle ones. All in all, on average, the anesthetized neural recordings offered a similar active electrode yield, higher SNR, as well as significantly lower noise and peak-to-peak voltage. The biggest takeaway is that anesthetized recordings are able to provide adequate data regarding the performance and reliability of MEAs. Similar AEY and higher SNR suggest that there are advantages to using anesthetized neural recordings rather than awake recordings for studies relating to performance and reliability. The main drawback is a decreased firing rate, which could potentially lead to undetected or ignored units in shorter recordings. Increasing the duration of the recording should reduce this effect. Regarding the depth dependency of the probe, the middle range of electrodes did not experience a significant change in firing rate like the others. A possible explanation could be related to the differences in density and diversity of cells within the different layers of the motor cortex. This research can be reasonably transferred to the chronic studies of MEAs. AEY and SNR can be analyzed under longer conditions to see if there's a significant change over time. If there is, it would be worthwhile to try and address solutions to maintain the longevity and performance of the MEA. Thank you so much for your time and attention. I hope you have a wonderful day.